I think, yeah, we should be live right now. Let me see.
За бүгдээрээ сайн байцгаана уу? Өнөөдрийн мэнд төргий хагас сарын өдөр манай судалгааны нээлттэй илтгэлд оролцож байгаад бүгдээрэнд нь баярлалаа. За ингээд эхний илтгэлийн маань модератораар Цэндэ маань ажиллан Цэндэ маань илтгэгчээ танилцуулнаа. За баярлалаа.
Great. Thanks so much. All right, so we have two talks today, and I think it's the first part of the research season of our deep learning summer school. And today we have Trapit joining us from Massachusetts. So yeah, first of all, Trapit, thanks so much for joining us. And I know it's late night there, so I'm sure all audience are gonna appreciate your time and the effort, and you're gonna enjoy, of course, the discussion. So yeah, Trapit is a final year PhD student at the UMass Amherst, advised by Professor Andrew McCallum. Trapit's research interests are mainly machine learning, NLP, and meta learning. So today, I think he's gonna talk about some of his work done in the meta learning field. So Trapit has interned at Facebook, Microsoft Research, OpenAI, Google Research, and in fact, Trapit has won the Best Paper Award at the ICLR International Conference on Representation Learning in 2018 by one of the work he has done at the OpenAI. So yeah, thanks again, Trapit, and please take it away.
Yeah, all right. Thank you so much for inviting me. It's a pleasure to talk to you all today. And thanks, Andy, for the introduction. So hi, everyone, and thank you all for joining my talk. So I'm Trapit, and I'll talk about our work on meta learning without label data to improve generalization of natural language processing models to new tasks with very few labeled examples. This is work in collaboration with my amazing collaborators. Feel free to stop me during the talk if you have any questions, or I can also take questions after the talk. So over the past years, machine learning has led to consistent improvements on many NLP tasks. And this has empowered numerous applications, including search, question answering, translation, voice assistance, and more. On evaluation benchmarks, large models and breakthroughs in unsupervised learning has led to state-of-the-art performance that seems to be beating humans. Here is a newer, improved version of this particular benchmark, and we are seeing some drops in performance for some of the models, but other newer models have quickly come up that still seem to be beating humans. Now, an important aspect of the high performance on a task is the amount of labeled data available to train the model. And here we can see, for example, on the natural language inference dataset, that models really require a large amount of data to perform reasonably, typically in the thousands. And such results, including many others, indicate that these models are really solving datasets and not tasks. And this is in stark contrast to how humans can leverage their past experience and generalize to never before seen concepts with even a single example. For example, given this one instance of an object category, you can easily identify which of these other objects are likely to be from the same category. Similarly, given this one instance of a relationship between two entities, you can easily identify which of these other entities have the same relation. So we're interested in such kind of few-shot learning ability, where models need to generalize to new, previously unseen tasks with very few labeled instances for the task. This is also of high practical utility. For instance, many real-world tasks of interest exhibit a long tail, where there is a large number of classes for which we have very few labeled examples. There are also new emerging labels over time, such as COVID-19, for which we like to make predictions, but we don't have a lot of labeled examples. Another example where few-shot learning is useful is end users of a cloud-based machine learning service, where we want to provide general purpose models that can be used by many customers for their own tasks. And they often have limited label data, as well as don't have resources to collect new data. This is also important when we want to learn across the long tail of languages or domains in text, or when we want to quickly adapt our predictive NLP applications to end users. In all these instances, collecting large datasets for every domain or language or user is challenging, but it is often possible to collect a few labeled instances. So few-shot learning ability is in general highly desirable. Now, the important question then is, how do we develop models that show better few-shot generalization to new tasks? So one approach that aims at learning general purpose representations and has been very popular recently is self-supervised learning. So the idea behind this is to use massive unlabeled data to perform unsupervised learning of a model. This is done by defining a self-supervised task that uses labels that naturally occur with data. For example, words in natural language. An example of such an approach that has been very successful is masked language modeling, where given a piece of text, some words are randomly masked, and the task is to predict the masked words using the model. Another approach that is often employed to learn general purpose models is multitask learning. Here, we assume access to a distribution of tasks with supervised data for learning. The idea here is to share statistical strengths by jointly learning multiple tasks with many shared parameters and a smaller number of task-specific parameters. This can also be done after self-supervised learning and has been shown to be effective for problems like domain transfer or learning tasks with limited label data. Now, typically, when evaluating models on generalization to new tasks, self-supervised learning or multitask learning constitutes the pre-training phase, and at test time, we want to use this model to make predictions on a task of interest. And this target task comes with some label data, and we then perform task-specific fine-tuning on this data to solve that task. For this, we will typically need some task-specific parameters like classification layers to make predictions in the outputs of the task. And the rest of the model parameters can be initialized from the pre-training phase, and the classification layers will be initialized randomly. These parameters will then be further optimized based on the loss on the training data for the task. And this optimization will introduce another hyperparameter, namely the learning rate, which is also important to set appropriately for fine-tuning. So this two-step process of pre-training followed by supervised fine-tuning can be suboptimal for future problems because there's an apparent train-test mismatch in the way the model is trained and how it is deployed at test time. To see this, note that this process introduces random parameters like classification layers and hyperparameters like learning rates, which are crucial for good performance and can be difficult to estimate robustly from little data. So we are instead interested in developing meta-learning methods, which will minimize this train-test mismatch for few-shot learning by optimizing the model initialization directly for future fine-tuning with few examples. Meta-learning works by leveraging prior experience of learning across many tasks with the goal of rapid adaptation to new tasks with few examples. This will enable learning an initial point for all parameters, including classification layers for new tasks, as well as learning rates for efficient few-shot fine-tuning. So this is an outline of the talk. I've discussed motivation for few-shot learning and will now provide some background on meta-learning before delving into our contributions. So in meta-learning, we assume a distribution over tasks for learning. Now, given a training data from the task, the goal of meta-learning is to learn a model that, given the training data and new examples from the task, can make accurate predictions on the new examples from the task. In order to learn the meta-learning model, the loss on the validation example across tasks serves as the training error that is used to optimize the parameters of the meta-learning model. Now, different choices of the meta-learning model give rise to different types of meta-learning methods. And these can be broadly categorized into three different types, which is model-based, metric-based, and optimization-based. Though this classification is not strict, and there are often hybrid methods that combine some of these properties. So model-based meta-learning is the most black box approach to meta-learning that makes minimal assumptions on the way the model uses the training data to make predictions. An example of such a method is a recurrent neural network that ingests the entire task training data and then makes predictions on any new examples for the task. A recent example of a successful meta-learning method of this category is GPT-3, which uses transformer as the meta-learning model. Since this makes minimal assumptions on the learning process, it can also be the most inefficient in terms of model size and the amount of data required for learning. In particular, GPT-3 required many billions of parameters and web-scale data for learning. The second approach is metric-based, which is related to the model-based approach, but adds a bit more inductive bias. So the idea here is to learn to embed examples in a metric space and make predictions on new examples by comparing them to the training examples. A prominent example is prototypical networks, which computes the centered embedding of each class in the training set as a class prototype and makes prediction by comparing new examples to each prototype in the metric space. The last is optimization-based meta-learning, and the idea here is to embed an optimization process into the meta-learning model. A prominent example is model-agnostic meta-learning, or MAML. The idea here is to use gradient-based optimization to solve each individual task and learn a shared initialization across tasks that can rapidly adapt to new tasks with few steps of gradient descent. MAML has a nice inductive bias of gradient descent that enables more efficient learning. It is as expressive as black box methods like recurrent neural networks and can be better at extrapolating beyond the training distribution as it uses gradient descent to adapt it to a task. Our work is based on MAML, so let's look at it a bit more closely. Here, F is a parameterized neural network, for example, a transformer model that maps sentences to labels. And the parameters of this network are optimized on a task training data using multiple steps of gradient descent. The final point of this optimization is then evaluated on new validation examples for the task. And the average of the validation loss across tasks serves as a training error for the meta-learning process and is used to optimize the initial point as well as the learning rate. Here, the task-specific optimization is also called as the inner loop, while the cross-task optimization is called as the outer loop. Note that the inner loop directly corresponds to fine-tuning that will be used on any new task at test time. So that minimizes train-test mismatch and optimizes the initialization directly for the few-shot learning process. Now, an important aspect of meta-learning is the distribution over tasks for learning. So where do tasks come from? The prominent approach to generate the task distribution developed for classifying images is to have a large data set with many classes and create tasks by sampling subsets of classes. For example, to create a two-way task, we can sample two classes, cat and dog, along with few examples for each class. We can sample combinatorially many tasks this way to create a meta-learning task distribution and train models for better generalization to unseen classes with few examples. This approach was also followed in NLP, for example, for the task of relation extraction, where tasks are constructed by subsampling relational labels from a pool of labels. So while this is useful to learn to generalize to new classes with few examples, it is not always feasible for all tasks of interest in NLP, such as sentiment classification or natural language inference. This limits training and evaluation to a very specific type of task, which is in contrast to things like multitask learning, which is often performed across many diverse tasks and also helps generalization with limited examples. So these limitations do not help in learning general purpose models that can generalize to new tasks and often even new domains. This was also seen in this FUREL benchmark in NLP, where meta-learning models demonstrated high accuracy, but when the test data was changed to be from a different domain than the training data, accuracy of these meta-learning models dropped by a large margin. So we'll instead try to develop more practical meta-learning methods that are not limited to learning from a fixed task dataset. So I will now discuss our contribution on meta-learning without label data. So we are interested in removing this limitation of meta-learning methods to be restricted to some supervised task datasets for training in order to enable really large-scale learning and improve centralization to many diverse tasks. We'll do this by leveraging unlabeled text for meta-learning and build on work in self-supervised learning, which has been shown to be highly useful for learning general-purpose representations. Our method will automatically propose combinatorially many meta-learning tasks from unlabeled text which will enable better representation learning, enable learning and better initialization of model parameters for few-shot learning, along with key hyperparameters like learning rates, and also avoid meta overfitting during the training process. So let's see how we automatically create classification tasks for meta learning. So to create an n-way task, we start by first sampling n words from the vocabulary and randomly assigning unique IDs to them. Next, for each of the sampled word, we sample sentences containing that word and mask out the occurrences of that word in the sentences. Note that each sentence has only one word type that is masked. And the label corresponding to the mask is the underlying word that was masked. So we use the ID assigned to that word as the label for the sentence. Finally, we construct the training and validation split for the task by splitting these sentences into two sets. This defines one task, and we refer to tasks generated this way as subset masked language modeling tasks, or SMLMT for short. Now, this process can be repeated for any n and any k to create n-way k-short tasks for meta learning from unlabeled text. This allows creating as many tasks as the number of subsets of vocabulary words, providing a really large distribution of tasks for learning. These tasks are related to closed tasks or masked language modeling, which has been shown to learn good representations from unlabeled data. However, note that these are sentence-level classification tasks, as there is only one word type per sentence that is masked, and sentences are grouped together into a class based on this latent word type. We'll use sentence-level representations from a model to make classification on these tasks, regardless of the position of individual masks in the sentence. So intuitively, note that all downstream classification tasks are in this distribution. If we can append the instances in the task with a blank filling prompt, along with a particular choice of target words for the task. Finally, note that the random assignment of IDs to the masked words ensures that the tasks cannot be solved without inferring this assignment from the task training data, which helps in avoiding overfitting in the training process. Now, these tasks can also be combined with supervised tasks to introduce further diversity in the task distribution. And we explore a simple approach to do this, where in each episode with some probability lambda, we either sample an SMLMT or a supervised task. So let's look at some evaluations. So we evaluated this approach where we trained a model on 2 million tasks sampled from the Wikipedia corpus. We use Wikipedia because it's the same corpus that was also used in our baseline BERT model. So results are quite comparable. We follow pre-training followed by fine-tuning approach for evaluation, where the pre-training is done either on completely unlabeled data or on a set of supervised tasks or a combination of both. And for the supervised tasks, we use glue tasks for training both the baselines as well as our hybrid meta learning model. Since few-shot performance can be sensitive to the set of examples in training, we repeat each evaluation with 10 different few-shot training sets. So we considered 3 baseline approaches for few-shot learning. We use the BERT model as the underlying text encoder in all the methods. So the first baseline is BERT, followed by fine-tuning at test time with randomly initialized classification layers. The second is a multitask trained BERT model, trained on the set of glue tasks. And the last is a supervised meta learning model that is also trained on the set of glue tasks. And we use a large number of tasks for few-shot evaluation. And the tasks here are highly diverse, both in terms of their output spaces, as well as the domains of the tasks. We have in total 17 different tasks for evaluation. I'm only showing a subset of these for illustration. So these are results on few-shot generalization to these tasks. This is, of course, a lot of numbers. So to give you an idea of the performance, we'll look at average performance across these tasks. So here I have the number of examples per label on the x-axis and the average accuracy across tasks on the y-axis. So first we look at unsupervised methods. So the blue line is the performance of the BERT model. Now, this orange line shows our proposed self-supervised meta learning method, which uses the SMLMT task for training. We see that this outperforms BERT fine-tuning. Oh, sorry. Something happened. My keynote crashed, it seems. Oh, okay, it's still there. Sorry. Yeah. So we see that this outperforms BERT with fine-tuning. Now, let's consider methods that utilize supervised tasks. So we look at multitask learning methods. And this green line here shows the performance of BERT trained with multitask learning. In particular, this model only fine-tuned the softmax layer for each task, freezing the rest of the model, which has been found to be beneficial when there is not enough labeled data for a task. And this red line now shows full fine-tuning performance. So interestingly, we find that the unsupervised SMLMT trained model performs better than BERT fine-tuning as well as multitask trained BERT models. This is now the supervised meta-learning model that was trained on the supervised tasks. This performs better on average than all of these methods, including the self-supervised meta-learning approach. So finally, let's consider the hybrid model, which combines both supervised tasks as well as self-supervised tasks for meta-learning. And this approach performs significantly better than all other methods for all k. And note that using unsupervised tasks in combination with supervised tasks also improved performance over the supervised meta-learning method. So one of the reasons the unsupervised tasks improve performance is by avoiding meta-overfitting in the meta-learning process. And to see this, we can look at the trajectory of the learning rates, which is a trainable parameter in these models, during the training process. So low or near zero learning rates indicate meta-overfitting, as the model does not need the task training data for adaptation. And we find that this is indeed the case for the supervised meta-learning model shown on the left, where most of the parallel learning rates converge to zero as we continue training. While utilizing SMLMT, in addition to the supervised tasks, most of the learning rates converge to large non-zero values shown on the right, indicating that the model is utilizing the task training data for adaptation. Next, in order to understand how representations differ across these models, we utilized CCA to compute similarity in model representations before and after fine-tuning on a task. So we show the representation similarity for each layer of the model on two tasks here. And we find that representations from the meta-learned model are more similar before and after fine-tuning, especially in the lower layers, indicating that the model is learning a better initial point. Finally, we also considered the effect of size of the model on few-shot performance. So for this, we considered two additional smaller size models, which are 25% and 40% of the size of the BERT-based model. And the orange models are trained with hybrid SMLMT tasks, and the blue models are trained with multitask learning. So we find that while larger models can lead to better generalization than smaller models, the proposed meta-learning approach also improves few-shot performance of the smaller models. And we can see similar results on other additional downstream datasets. This can be particularly useful for scenarios where we need like small memory efficient models that also show good adaptation at test time with limited data. All right, so this is an interim summary. So we introduced an approach to use unlabeled data to create tasks for meta-learning. This now enables large-scale meta-learning from unlabeled text, which wasn't previously possible. I can stop here to take any questions, or I can continue and take questions at the end.
Well, so yeah, there is a question. So let me read it out. I'll show it here. So what is the, this is question from Anat. So what is the difference between multitask learning and meta-learning? A high-level explanation would be great. And second, in what situations do we need meta-learning? So two questions we have from Anat.
Yeah, so that's a great question. So like both of these are like quite highly related in many sense. So both require like a distribution of tasks to learn from. In that sense, they're quite related. So what multitask learning does is like it tries to find a point that's like equally distant from all tasks that you're learning from. Whereas what meta learning does is like it tries to find a point from where you can reach any new task much faster. So it tries to optimize for more rapid adaptation to tasks, and as a consequence, it has like this nice property that when you get new tasks that are still from that have not been seen but from the same distribution, then you can quickly adapt to those tasks and solve them much more faster in terms of like number of gradient descent steps required to solve them. Yeah. What was the second part of the question? I forgot.
Sorry. So let me show it again. The second question is, in what situation do we need?
Yeah, so I sort of like combine those two. So like if we typically require like meta learning when we are thinking of like not just solving the set of tasks that we have available, but also like trying to generalize beyond the set of tasks that we have available to things that are related to that we have seen earlier, but not exactly the same. So like for example, solving like new domains of things that we have seen earlier, or like in our case, like solving new classification tasks that we haven't seen at all previously.
Yeah, that's really great explanation there. Just to add, like a very high level, I guess, answer. So in meta learning, we basically care about the learning process itself, right? So we want to learn how we learn, so that since we know how to learn, then when we have a new task, we apply that knowledge. So it's not about learning the just typical one input distribution, let's say, for one task. It's about how we learn to solve different tasks. And when we have a new task, we use that high level knowledge to solve that task quickly. So one of the goals in meta learning is to sort of learn the similar commonality across these different tasks, also like maybe the similarity between these tasks, and apply this knowledge when we have a new task, right? So just do it there. And we have other questions from Casey. Oh, sorry,
Sorry.
yeah.
Okay.
Yeah. So yeah, what's the, can you compare basically meta learning versus multitask learning versus transfer learning? Also, the second question is how to solve black box adaptation. So
So I think these are like all quite related. So I think of like transfer learning as like a bigger umbrella, which covers like many methods, like apart from like just multitask learning or meta learning, many other things as well. So I'll think of like multitask learning as a type of transfer learning. Similarly, I'll also think of meta learning as a type of transfer learning, at least like applications of meta learning for transfer learning. So these are all quite related. So they are all like approaches that can be used for transfer learning. And how to solve black box, I'm not sure what, can you, whoever asked this question, explain what they mean by how to solve black box adaptation?
yeah, I'm also not clear as well. Casey, would you care to elaborate a bit in the comment? Yeah, so black box adaptation is basically something we mentioned during the model-based meta learning, right? So it's sort of,
Yeah,
we
okay,
learn
yeah,
this sort
I
of.
see. Oh, okay. I see. Yeah. So those black box meta learning models, like they don't really have any adaptation built into them, like the kind of mammal model that I described. So there, the idea is that you would, for example, ingest all the training data that you want for a task. So for example, think of an RNN that like sequentially reads all your training data one by one, and then given any new example, would just use the training data that it processed so far to make predictions on that new example. So it's a black box method because all the learning to learn is like happening inside the model itself. So the recurrent neural network is like trying to utilize the training data to solve new examples for that task. And you do this like across many different tasks. So the model is internally learning a model of like how to solve tasks, which is not very explicit, like fine tuning. That's why it's called like a black box method.
Right. So also it's like really hard to interpret the learning process itself.
Yeah.
Right. To compare with the optimization-based method, for example, in Trapit's last few slides, you mentioned about you were able to basically interpret the overfitting or meta overfitting by looking at the learning rate itself. That's a really nice insight to have there. But when we talk about black box adaptation or model-based meta learning, so it's hard to see that because it's a bunch of weights that we find during the optimization, right?
Yeah.
Okay, thanks for the question. So we have next question over here. Let me show it here. So you said the model was sensitive to the test data. Could you elaborate a little bit more on that? Thank you. Yeah.
Okay, I don't remember saying that model. Oh, I don't. So that's not what I said. So I said that the model is sensitive to the few examples that are used for each few short task, right? So since it's like a k-short training k-short scenario where you have only k examples for a task, it's sensitive to what particular k examples you have for that task. So in order to like have our evaluation numbers be robust to such kind of like noise, what we did was like we sample many examples of like k-short tasks for any given task of interest. Like for example, sentiment classification, we'll sample 10 different data sets of k-short tasks, and we'll run our model on like all 10 of those and evaluate like how well it does, and then find an average and standard deviation for like, what's the model performance and how much it varies. Um, so that's where the sensitivity comes to. So it comes to the particular examples that are there present in the training data for the task.
Yeah, that makes sense. Yeah. Okay. Next question is from Anna as well. Yeah. So we know that transfer learning-based model, for example, BERT, is being deployed in Google Search. Do we have an example for meta-learning-based models being deployed in real-life use cases? Thanks.
Yeah, that's a good question. So yeah, like in some sense, like you can think of like models like GPT-3 as well as like meta learning methods. So like, people have been starting to use GPT-3 for various kinds of things. It's like a model-based approach to meta learning. So you can think, so that's maybe one example of like meta learning methods being deployed in real life. But I think like historically, like a lot of meta learning methods have been like, developed in like more academic settings with like smaller data sets that don't directly have much practical value so far. But we are increasingly seeing like more deployment of these things in like real practical applications now. And some of these methods that hopefully we are talking about today can also be used to improve such applications in the future. And apart from like text, which is what I'm talking about today, I think there are instances in like things like robotics where there are more practical use cases of meta learning as well, and people have found real applications of meta learning there as well.
Yeah, great. Thanks, Anat, for the nice questions. Great question. So, Casey say thanks so much. And yeah, there's the fourth question from Anat as well. So let me show it and read it. Is there a way to interpret model predictions besides using the Shapley or limit line values? So yeah, it's really, so that's
I
the
see.
question. And yeah, it sounds to me like bit off topic, or I don't know.
Yeah. Yeah,
Please,
so
yeah.
I guess I haven't been talking about interpretability at all here right now. But yeah, I think all of these things that you're describing, like Shapley values, align values, like they're all good ways to do model interpretation. I feel like that might be a topic for some other talk in the future.
Yeah, okay. Yeah, great. All right. Thanks so much. Yeah, those are really nice discussions, and also questions. Please keep them coming so
All
that
right. Yeah, thank you so
we'll
much
have
for the questions.
some nice.
Uh,
Yeah, please go ahead, Trapit. So yeah,
Yeah, thanks. So let me
yeah, thank
continue
you.
the next part of the talk. So we talked about this like unsupervised method to create tasks from for meta learning. So we're now going to look more closely at the self-supervised approach to task creation and propose modifications that will try to improve this task distribution. So this was the self-supervised method to create meta learning tasks. And here this first steps involves sampling a set of n words, and these words then serve as latent classes for a task. And previously, we used uniform sampling over the entire vocabulary to create tasks. So we are interested in exploring how the task distribution changes as we change our word sampling process. And can we control the difficulty and diversity of tasks through modifications to this sampling process? So now word distributions in natural language corpora follow this kind of like exponential distribution. So if we sample words uniformly, this gives equal probability to all words and puts a much larger weight on sampling rare words compared to more common words. An emergent alternative then would be to sample words proportional to the log frequency of occurrence in the corpora, where the log flattens the heavily skewed nature of the distribution. Another approach could be to find some semantic grouping of words into concepts or topics. And given such a grouping of words into topics, we can look at two alternatives to selecting words for a task. First, we can sample all words from the same concept for a task. This approach allows us to create more difficult tasks, as related words can be more difficult to distinguish, and also allows us to create more diverse tasks by covering a wide range of concepts across tasks. The other approach is to sample all words from distinct concepts. However, this can lead to sampling of completely unrelated words, which might be easier to distinguish. So how do we group words into semantically related concepts? There are a number of options. We can use a curated database like WordNet to get some categories, or we can automatically extract them from the corpora using some unsupervised approaches like topic models or clustering word embeddings. We consider automatic approaches as they have high recall over vocabulary words present in a particular corpus. And in particular, we use clustering of words to find topics. There are many off-the-shelf word embedding methods available with pre-trained word embeddings. In particular, we use fast text for embedding words. So given a clustering of words in the corpus, we have two approaches to sample labels: intra-cluster sampling, where all words belong to the same cluster, or inter-cluster sampling, where all words belong to different clusters. Now, the methods discussed so far create an offline fixed set of tasks for training. However, an interesting aspect of being able to synthetically create tasks that we can potentially control the order in which tasks are presented to the model during training. So if we can control the difficulty of the tasks during the training of the model, we can provide a natural curriculum for learning from easy tasks to increasingly harder tasks. Now, the word clustering approach can help create more difficult tasks, as we'll also see empirically, but the previous methods used an offline creation of the tasks using some pre-trained word embeddings. So one way to get a curriculum over task difficulty is to find representations of words from the current state of the model, and then again cluster these representations. So at iteration T, for every word, we can sample some blank filling sentences for that word that will be used in our self-supervised tasks. We can then embed these sentences using the current parameters of the model and take the average representation as a representation of the word. These can then be clustered to create a word representation clustering at step T. And words closer in this representational space would be harder to distinguish by the current model and will lead to more difficult tasks. And this can be done repeatedly during training to continually find a hard set of tasks for the model. We can also mix in easy tasks from either uniform sampling or an offline clustering, as we discussed previously. So here lambda is a mixing ratio of dynamic and static tasks, and gradually annealing lambda from 0 to 1 over training steps will lead to a curriculum from easy tasks to hard tasks. Now, of course, computing these representations for the words and reclustering at every iteration can be very expensive. So we instead consider clustering after every few iterations and use a slightly older version of the parameters for finding the hard tasks at a step T. So this can be done in parallel without halting the main training process. Now, we developed this particular approach to getting unsupervised tasks that was based on these close-style blank filling statements. So let's instead look at another alternative approach to create task distribution from unlabeled data, which is inspired by some research in computer vision. The idea here is to have a large collection of images and embed them using some unsupervised pre-training model for embedding images. Then we can cluster these images using a clustering method. And now tasks can be constructed by using the cluster assignments as a set of classes for the images. So we can sample from the set of clusters to pick a subset of the clusters and sample some instances from them to create tasks. This can be extended to sentence level classification for natural language processing. And since pre-trained sentence embedding models have become increasingly good at generating high quality sentence embeddings, we can embed and cluster sentences to create tasks. So here is an example of a task that can be created this way. Again, we can sample with sample tasks with any number of classes, and combinatorially many tasks can be sampled using a high number of clusters. So we get all these different ways of creating task distributions based on different ways of sampling words in SMLMT or based on clustering sentences. So let's now compare like all of these distributions for over tasks for meta learning. So first we look at how these different task distributions relate to each other. So what we'll do here is we'll train models on a particular type of tasks and then evaluate how well they do on another type of tasks. So on the rows, we'll have model trained on a task distribution, and on the columns will be the target tasks on which they're evaluated. So first, this is uniform sampling in SMLMT. So while this does well on frequency and intercluster tasks, there's a large drop in accuracy on the intercluster tasks, which drops further when the tasks are from a different domain, like Common Crawl. Also note that it can already perform well on sentence clustering tasks, even though they are from a different domain. Next, we look at frequency-based approach. This performs similar to uniform sampling with slight improvements in accuracy. Now we look at models trained on the intra-cluster tasks. This performs well throughout, though the performance on intra-cluster tasks from different domain still suffers. Finally, we also look at the model trained on sentence clustering. This performs much worse on word-based SMLMT tasks, indicating differences in the two task distributions. In particular, performance on intra-cluster tasks is even worse. So all of these results indicate that the intra-cluster tasks are more difficult than the other tasks, and training on more diverse domain is important, as shifting the domains leads to performance drops even when the type of the task is same. Now let's look at some real evaluation on overall average accuracy across tasks to see how these changes affect downstream performance. So first, the sentence clustering approach performs worse than SMLMT with uniform sampling. This is followed by frequency-based sampling, which already improves performance. And then SMLMT with clustering-based word sampling performs even better. When we introduce curriculum into the clustering-based tasks for learning, this improves performance a little bit more. And finally, using a more diverse domain from Common Crawl for training also leads to large gains. We also compared our results on the Furel 2.0 benchmark, which is a few short relation classification benchmark. So we evaluated the unsupervised models directly on the test set without any additional training data on the training data for, available for this benchmark. And we see competitive performance with supervised meta learning models in one-shot setting, even though our model was not really trained for the one-shot setting. And in five-shot setting, we see better performance than even the supervised models. Finally, we can also further train this unsupervised model on the supervised training data that is available for this particular benchmark, and this leads to the best overall performance. So to summarize, we introduced an approach to use unlabeled data to create tasks for meta learning. We improved this further using ideas like clustering and curriculum, and saw that this approach is even better than using a naive clustering over sentences to create tasks for meta learning. We show that this helps ameliorate meta overfitting, learns generalizable representations, and improves few-shot learning performance on a range of tasks. This now provides a practical method for large-scale meta learning from unlabeled text, which wasn't previously possible. In the future, it will be interesting to explore uses of such self-supervised task distributions to potentially help provide meta trading tasks for many other meta problems in NLP. That's all I have. Thank you so much for your attention. I'm happy to answer any more questions. And in case we can't get to your question today, like feel free to shoot me an email at this address.
Cool. Yeah, thanks so much, Trapit. So, yeah, so we have a question from Oyank. So let me show it. What types of cluster methods could be used to cluster the text?
Yeah, good question. So we just used k-means clustering, and we use like Silhouette ratios to like find like some values of k for doing the for selecting what number of clusters to use during the clustering. We haven't really explored any other methods than k-means, but yeah, it could be other methods could also be explored.
Yeah, I think, yeah, so we have this sort of hierarchical clustering algorithms as well, right? Like somewhere we also discussed about that. So that sort of hierarchical structure could provide us some sort of, rich task, this
Yeah,
sort of
definitely.
elliptic structures. So that would be interesting to explore too. Yeah.
Yeah.
Right. So do you have? Says thanks. It's
Can you say a few more words about sentence clustering?
Like explain it again. Sure.
Do you look at the sentence or the words in the sentence?
Yeah, so we look at the sentence. So we use like some sentence embedding model. Like for example, in this we use like CentBERT, and we take the entire sentence and just embed it. And so we get like so we take like all about 1 billion sentences in Common Crawl, and embed all of them using this approach to get a huge bank of sentence embeddings. And then we run the same k-means algorithm on this sentence embeddings to get these clusters. And then, yeah, you can essentially treat these clusters again as like latent classes and create tasks by, picking a small number of subsets of clusters and using that to create these meta learning tasks.
Thank you.
Yeah. To me, like the idea of curriculum, learning this curriculum is interesting. And you mentioned about, estimating the difficulty of task or the input by looking at the model's representation, right? Internal representation.
Yeah.
Could you elaborate a bit on that? Does that sound very interesting? But I could not completely get the idea. Yeah.
Yeah. So essentially, like the idea is that sentences that are like closer together, words that are closer together in the embedding space, based on the model's representation of those words, would be difficult to distinguish amongst. So we can continually find like what sets of words are hard to distinguish by clustering these, and words that are in the same cluster would be more difficult to distinguish amongst for these tasks, right?
Oh, I see. Yeah, that's very clever. I mean,
yeah,
it's a dynamic process too, because the model is going under optimization. So you need to. Okay, it sounds like okay, cool.
Yeah. So we saw some of these results as well, that the clustering. So if you look at like intra-cluster column here, like there's always like a drop in accuracy, which indicates that these are like harder tasks for any of these other approaches. So this was based on like a static clustering, and so the dynamic clustering idea essentially just like makes that dynamic, where you keep changing this clustering based on the state of the model during the training.
Yeah. Cool. Okay, we have another question from Anna. Anna is one of the organizers of the summer school as well. So what's the advantage of sentence embeddings over word embedding?
Yeah, so as it turns out, like empirically, there is no advantage right now to this method. So this is like, this is a completely other alternative to using like close style things, which have lately become like very popular in NLP. So which is like just take sentences directly, embed them and cluster them. So we like going in, like we didn't know that this would be worse. We were expecting that this might be like comparable or like even better, but it turns out that it's not as good as doing the close style task creations. One of the reasons for that could be that like when we do this clusterings, like we find that often distinguishing sentences of one cluster versus another cluster is very trivial based on even things like simple word counts, because these are like very topical clusters, and words in one cluster would have like certain word choices, and words in another cluster will have completely different word choices. So it becomes very trivial for the model to like distinguish these word clusters easily. So it didn't turn out to be so well. There are things that one can do to improve this further, like doing, like as Sandy mentioned, doing like hierarchical clustering. So if you do this over sentences, like it could potentially improve it, but it's a lot more expensive to do this over sentences, because the sentences are in like billions, whereas words are in a few hundred thousands. So we haven't explored doing like a hierarchical clustering on these sentences yet, but if someone's brave enough to do that, that could be one way to improve this further.
Right. Yeah. Cool. Yeah, I would go on to discuss a lot about this, but yeah, I know it's very late there. It's almost 2 a.m. in the morning in Massachusetts, right?
Yeah.
So yeah, thanks so much, Trapit. Yeah, it's very interesting talk, and we had a lot of very great questions, and people definitely enjoyed it. So so we have the one last question, and I promise you, this is the one last question, and then you can go to bed.
Sure. Yeah, no worries. Happy to answer.
What are the potential use cases? Do you see that this model is employed in the future?
Yeah, excellent question. So I mentioned to like many potential applications in the beginning of the talk. So like one direct applications could be like, for example, machine learning as a cloud service, where the idea is to like serve machine learning models to end users directly. And often like these users would want to use these models directly on their application with like maybe little amounts of data over which they want to fine tune these. So that's one direct application. So our evaluation methods also like sort of reflect that kind of a setting. Another application could be like a domain transfer. So like you want to apply some trained models to like new domains, and again like there is like a long tail of domains. Like we generally don't think about this often a lot. So like for even in PubMed, there are like many domains within PubMed itself, and they differ in like their linguistic properties and so on a lot. And models don't usually generalize to new domains so well. So using these like few short learning methods, like we can do some domain transfer much better by like having a smaller number of labeled examples from that domain and transferring to those domains. And other applications that we haven't explored yet but are also like possible are like applying these across languages. So learning like a unified model across languages that can help solve tasks in like new languages, where you have like little amounts of labeled data on that language, but you can potentially have like much more unlabeled data for those languages to learn from. So these are also applicable in those scenarios. Other things could be like adapting these models on device to applications like smart reply, or typing predictions and so on.
Yeah, cool. All right. Thanks so much, Trapit. And yeah.
Thank you so much for inviting me and all the great questions. It was a pleasure to talk to you all.
Yeah, it's a wonderful talk, and thanks so much. Right.
Thank you very much.
Thank you.
Bye.
Okay, thank you.
So we have...
За манай дараагийн илтгэлийг тавих хүмүүс маань бэлэн болсон байна. Одоо ерөг оруулчих тий. Broadcast руугаа.
За.
Дэлгэцийг оруулчих уу? Өөрөө оруулж байгаа юм болов уу?
Дэлгэцийг нөө. Yeah. Okay.
Тэ оруулсан баг тий. За манай дараагийн илтгэлийг тавих хүмүүс маань бэлэн болсон байна. Дараагийн илтгэлийг сайнаа маань share хийн. Тэгээд илтгэл тавих хүмүүсээ танилцуулаад явна. За баярлалаа.
Okay. So thanks for coming here for such a late hour, also such an early hour, to talk about the law research multi-language machine multilingual, machine learning translation, which is really important in Mongolia because Mongolia is one of the low resource languages. So I think it's going to be great. And so today we have two great people from Facebook AI Research. So Angela is a research scientist at Facebook Paris now. She just graduated the PhD from INRIA, and before that, actually, she was working at the Facebook as engineer. And she took her PhD from Harvard. And we also have Vishrav, who is a research engineer at Facebook AI, and he also works on language processing, machine translation, and he earned his master's degree from CMU, Carnegie Mellon University. So thank you for coming, and I guess yeah, we can start. Yeah.
Perfect. Thanks a lot. Just wanted to check if people are able to hear me. Am I audible?
I can hear you.
Awesome. Thanks everyone. Then. So first of all, thanks a lot, Saina, for introduction. For myself and Angela, and good morning to Paris folks. Not sure if anyone else apart from Angela are attending or not. Good afternoon to everyone in Mongolia, and good evening.
So we're actually streaming in Facebook. So there are people watching in Mongolia. Yeah, in the afternoon.
Perfect. And good evening to anyone in case if they are in Bay Area time zone apart from me. Awesome. So today myself and Angela will cover a very important topic, which is about low resource machine translation. So yeah, let's get started. Sure. So what we need to understand is that from this talk, I want us to gather three things. The first thing is that translation helps to connect people across languages, but in order to do so, there are many challenges that needs to be solved. So that involves learning under low resource regimes and scenarios. And what we have to understand is that with the right type of data in hand to track progress and to train these models, and with the efficient modeling techniques, we can achieve this, and the performance of low resource translation has improved significantly because of that. In another scenario, what we can assume is that language can be a barrier for communication across various communities and various people, and thousands of people face this every day. So with the friends from abroad, or let's suppose our grandparents, if we want to communicate with them who speak in different languages, or in case if you're visiting a particular place and you want to make sure that you mingle in the local market or are aware of any kind of sales that are happening in that area, you need to understand the local language, and that's where machine translation, especially for low resource languages which has not been developed before, comes handy. So in this case, translation can definitely help. And on a personal note, I've been very fortunate to make friends, which is pretty evident today that I'm connecting to a lot of folks who can speak variety of languages. But without a proper language, imagine the reach that we could have in case if we were able to translate and live stream the particular talk that we are giving. We can even increase the reach of this talk exponentially. So this is the power of machine translation that can provide and help the knowledge to spread across many cultures and communities. Now let's focus on the setting of low resource machine translation, in which case since 2016, what we have observed is that a lot of advancements have been made in the field of neural machine translation. However, this is a very big challenge when we have to deal specifically with low resource languages. And this has been identified as one of the 6 grand challenges for neural machine translation. How do we address this problem in general? How do we make low resource languages really low resource? Should we bring in more data, or should we just improve on the top of the current existing data that we have, or should we invest more into modeling? So these are few questions that we will try to answer in this presentation. Traditionally, we have seen that sequence to sequence models can learn to translate well if there is sufficient amount of parallel data available. However, there are approximately 6,000 plus languages in the world, and we have not seen enough parallel data for most of them. Nowadays, the neural based models are powerful, and they can learn how to translate well if they are provided with sufficient amount of data. Some translations in WMT competitions can even have near human level parity performance of the translations, but since there are more than 6,000 languages, we need to understand that are we doing enough justice to the remaining set of languages or the long tail of languages that we are not covering, that do not even have enough parallel data to train on. So for these set of languages, we have coined, the community has coined a term low resource languages, because there is not enough resource in terms of training data available to train these languages. And by taking a look at this histogram, we can see that the number of parallel data, or bytex as we say it, reduces drastically if we go towards the lower tail of the languages. Perfect. Now there are several challenges, for improving the translation system for low resource pair. As I mentioned before, that the amount of training data is limited, and what we also need to understand is that it's just not the amount of training data, but also the lack of monolingual data present. Because if you go towards a set of language which is not spoken by a lot of people, and there are not enough resources, you will start noticing the dearth of monolingual data in that domain as well. And another point to note here is that if we have good amount of parallel data present, can we confidently say that do we have evaluation data also present for that particular set of languages? The answer is no. That's a very wrong assumption to have, and we will provide more details later in the presentation on that field. Another point is domain of the data is limited. So we know that neural models are sensitive to the distribution between test and training data. So for example, it is very hard to translate news if we only have Bible data. Just a point to note here is that Bible is present in a lot of languages, so that's why it's easy to extract some amount of parallel data, but then the domain is very different in that case. This problem becomes really worse when we move towards low resource domain, because low resource languages are often very different, which makes the translation task even more difficult. This actually motivated us to work on the evaluation problem first, so people could track progress in low resource languages. And as a result, we worked on creating this wonderful Flores dataset, about which we'll provide more details in further slides. But it actually currently includes two, in the first version, it included two low resource languages, which was Nepali English and Sinhala English in the first iteration. And we have recently released a many-to-many evaluation dataset that covers 101 languages. Awesome. So to recap, some of the current progress in the field of low resource machine translation includes concerted efforts on improving the translation quality of real low resource languages. By real, I'm trying to emphasize on the fact that the condition for low resourceness is not emulated, because in the past we have seen that people have tried to make progress on the so-called low resource scenarios by undersampling training data present for high resource languages. This is actually not true, because there are a lot of there are a lot of variations that can happen once you move towards low resource languages, and that poses additional level of challenges. Secondly, we want to move into a world wherein we are not relying on English as a pivot language. So Angela will cover more details about this point in her presentation. And what we also need to understand is the gaps between the training data sets that we have for these variety of high, medium, and low resource languages, and how can we bridge that gap so that the performance of the end model doesn't suffer. And lastly, more focus on having a robust evaluation data set and reliable benchmarks upon which people can iterate on and measure the performance of their systems. Awesome. Let's move to the next section, which includes talking more deeply about the Flores project. So the first question that we are trying to solve as part of this project is, how can we make our models make models without evaluation? This is almost impossible, right? Like, because if we don't have any test data to evaluate our models, we would not know how well are we doing, how well are we doing on the test data set, or like, you know, we would not be able to gauge the performance of our model that we have just trained. Secondly, we want to understand that how can we evaluate through any direction. One of the major challenges that this requirement or this motivation comes from the fact that a majority of the languages or the test sets that are present are always translated into English, or start from English and get translated into any other language. So how can we break this barrier in which we have to always rely on English in order to, as the pivot language, and in order to get the performance of a many-to-many language translation scenario. Perfect. So this brings us to summarizing the requirements that we had gathered for this project, which was we wanted to focus on low resource languages. We want to have an evaluation data set that covers many-to-many languages, and we don't have to rely on English for the performance. And we want to cover a variety of languages that range from high, medium, and low resource spectrum. So we chose this magic number of 101 languages to begin with. Additionally, like evaluation of machine translation within the last few years has also seen that like a lot of techniques have been used to perform or make the translation models even better in terms of different domain. So this is also crucial, so that the evaluation data set that we create has seen like, you know, a lot of domains coming from various topics like news, books, or like or in terms of like any other domain that is not usually covered in traditional evaluation data sets. And last thing is we also want to pose like, or make the evaluation challenge even more robust in terms of like understanding if there are actual intricacies that get messed up when we are moving towards the world of document level machine translation. So for example, this is actually currently not possible without the presence of good quality evaluation data set that preserves document level context. So this is another motivation that we have to basically create the benchmarking data set or test data set that has context for the document level as well. And lastly, it's not just about like performing it's not just about measuring the performance on the end test data set, but also reliably, or also being in a position to reliably measure the performance of your translation model on a variety of metrics, which may include like gender bias, or like, you know, profanities, or how well are we doing on fact checking or named entities, which is what Angela would cover in the next set of research sections. Perfect. Another thing is, in order to facilitate research and provide the research community with more additional metadata that can come along with the test sets, we have also included like the URL, topic category, and also if there was any particular image present along with the test set, so that this can also facilitate research in multimodal translation. Perfect. So here I will provide a very brief overview of how does the evaluation workflow look like. That we actually use to collect and annotate the training, test, and the dev data set for the Flores 101 project. So in this case, the process of Flores actually led us to rethink how we see the translation generation process. So particularly for low resource languages, we have to implement both automatic and manual checks, and the main reason for that is to provide back and forth between the different vendors that we were considering. So in this scenario, assume that we have a document that comprises of various sentences using which we want to annotate. So we would first ask our translators and send it to a particular vendor to translate these sentences into foreign language, and then we would perform one level of automatic checks in order to understand if there was something that the translators missed, and then we would pass on the translations that we have thus far collected to another vendor that would perform human evaluation, and in case if they find something missing in terms of the quality of the generated translations or any context which is missing, they can perform post editing, and then this we can go through this loop multiple times till we feel that a considerable quality of translations have been achieved. A point to note here is that as part of the automatic checks, we also want to ensure that the translators are just not cheating and not providing us with machine translations from many popular open source or like openly available translation engines on the web, because this is apparently true for low resource languages, wherein it becomes really difficult for either the vendors themselves or us to check in case if there was something, in case like if the translator actually generated the translation or they ended up using one of the engines present on the web. And once we have a satisfactory guarantee from both of these loops, that's how we would consider the generation of the annotations to be complete. The dataset has already been released on June 4th in the WMT shared task, and feel free to visit this link to get more information about the shared task that we have organized as part of WMT this year. And yeah, there are 3 tracks available for people to try, and we also support automatic evaluation of the translation through a compute server. So yeah, please to visit the link and get more information about the shared task and download the dataset. Perfect. So even thinking beyond Flores, there were some languages that we partnered with a group for basically generating translation level data set for based on NLI, and this included actually really low resource languages covering Quechua, Aymara, and many native Indian American languages as part of this effort. So yeah, so this actually provided us with a lot more variety and direction about how can we go about scaling Flores to even more languages. So yeah, we'll keep you updated about the next set of progress there. Perfect. Now I'll hand over the presentation to Angela, and she'll cover the remaining section.
All right. Thanks so much, Vishrav, for kicking us off. Everyone can hear me? Okay,
yeah.
Great.
Yes.
Okay, great. So Vishrav started us with a great section on how can we measure the quality of different translation models. So now I'm going to change topic and discuss, given that we can measure quality for different translation models through data sets like Flores, how can we actually build models for translation? So this is kind of like a high level view of what worldwide translation demand looks like. And so how you want to read this chart is that the color reflects like the amount of translation demand. So darker color means that people kind of want translation more for that direction. And the languages are listed on kind of the X and the Y axes. So for example, kind of very relevant to myself personally, since I live in Paris, but mainly speak Chinese with my family, it's like, one cell here would represent a direction, for example, from French translation as the source into Chinese. And so worldwide translation demand, it looks very varied, right? People want translation through all different types of directions. So of course, when I left China and moved to the United States, I mostly cared about learning English. So I did a lot of Chinese to English translation. But after I came to France, a lot more like Chinese to French or French to Chinese. There are a lot of countries, for example, like Vishrav is from India. I think the Indian constitution recognizes 20 different official languages in India. So, throughout the country, there's a lot of translation demand, between different languages in India that really doesn't incorporate English. So even though worldwide translation demand actually looks like this, what most people are producing in terms of translation is that it looks basically like this, where you only consider translations in and out of English. A lot of this is because there's a lot more training data in and out of English, right? So for example, if you think about translation data sets that have been funded, for example, by the EU, a lot of it is out of French into English or out of German into English. And so historically in research development, people have mainly focused on kind of English-centric translation. And so the major question is how can we bridge the research world, which mainly focuses on English-centric translation, into something a little bit more realistic that reflects what real-world translation demand actually looks like and how translation is used every day around us. And so in this portion of the talk, we're going to talk about how do we model something that looks a little bit closer to real world translation and takes us out of this kind of English-centric mindset, which is perhaps ironic given that this talk is in English. So when we talk about multilingual machine translation, there's kind of three broad categories for this type of model. And so the first is called many-to-one. And the idea is that here there's many different source languages and one target language, which we're always trying to translate into. So you can see that depicted on the left, where we go from like Chinese, French, Thai, or Nepali into English. The second world is what we call one-to-many, where you have one source language, let's say English, and we want to translate into a bunch of different target languages. And these two together form kind of the English-centric translation world, where we basically translate in and out of English. And the final, which you can see all the way on the right, is really the focus of this talk, and kind of how do we have modeling techniques and data that really enable this, which is that, forget about English's kind of more special status, right? Like here, all of the languages are equally treated, and so we have this what we call truly many-to-many translation. And so the major question we want to tackle is, if we want to do many-to-many translation, it becomes very difficult to develop specialized translation techniques or specialized translation models for every single direction. So if we only want to do 100 languages into English and 100 languages out of English, you can imagine that's kind of 100 models and then 100 models, so you have 200. But if you really want to do many-to-many, this is kind of like a multiplicative problem, right? So you want to do like 100 times 100, and so the number of translation models you need to build becomes kind of very large very quickly. And so people have turned to multilingual machine translation kind of as the promise for development in this direction. And multilingual machine translation tries to not develop specialized models for each translation direction, but kind of group it all into one model and consider really like, how can we get the best performance for all of these different translation directions, but only using one model? And I want to note that even though Vishrav and I are really, academic researchers, this has a lot of benefit for actual practical translation, right? Because if you were actually trying to deploy a machine translation system, it becomes very intensive if you wanted to personally maintain like so many different types of models. So actually this has a lot of practical benefits as well if it actually works. And so we start first with training data. So Vishrav talked a lot about evaluation data. And so that's how you measure the quality of your translation system after you've been able to develop the model. But how do we actually develop the model? And this is something that Vishrav has actually worked on, and he is the expert. He has developed two great projects that are actually open source, so you could download this data, and we'll provide a link afterwards, called CC Aligned and CC Matrix. And the idea of this is that translation models are often trained off of human translations. So when, for example, the EuroParl project started, it's a data set of 20 different European languages. It's basically based off of European parliamentary data, where in European parliamentary debates in the EU, there's many different member countries, so they have provided like human translators for all of their sessions, and so their parliamentary sessions are automatically translated into all of those languages. But when we talk about scaling translation beyond that, we don't have human translators, like millions of them, providing training data. And so people have turned to what we call these large-scale data mining efforts. And the idea is we start with Common Crawl, which is an open source dump of the web. And we kind of look at the web and we kind of try and extract the textual data from it. And so once we extract the text, then we want to try and find matching content that could be a translation. So how is this possible? This is enabled by multilingual embedding systems. So all of the sentences of the web are basically extracted and embedded into one system. And then we try and find content that overlays itself in the embedding space. And this matching content could be a translation. And so this produces a very noisy translation training data set, right? Like no one has gone through and validated that every single one of these sentences is a translation. But empirically, we find that this works really well. And most importantly, these mining efforts are incredibly large scale. And so we can mine hundreds of millions of aligned sentences for a lot of major translation directions. And so, how do we actually decide what to mine? So if we do 100 by 100, the number of mining directions also drastically increases. And so we choose to mine data in two different kind of strategies. The first is bridge languages. And these represent like the most common translation directions that there's a lot of demand. So for example, in India, a lot of translation goes through Hindi. In Africa, a lot of translation goes through Hausa, Swahili, English, and French. In the EU, central languages are French and German. In South America, Portuguese and Spanish. And so these we term bridge languages. And so these languages are kind of represent the major languages of the world. And so we mine data through all of them. Then for more specialized languages, we basically try and mine related languages through a family. So for example, what's shown here are Germanic languages. So for example, in Scandinavia, they speak Danish, Swedish, Norwegian. And so for those languages, there's not that many people who speak Danish in the world, but there's a lot of translation demand in that region. For example, from Danish to Swedish, from Swedish to Norwegian. And so we create training data for that language family. And so this way we try and naturally reflect people's translation demand. And so this produces data that looks a lot like this. So the y-axis here is the number of sentences that we're able to mine. And the x-axis here is a few major languages. And so the gray bar represents the data that we can actually mine through English. So of course, like all of English is the gray bar. However, actually, if you notice for a lot of the other languages, the amount of data you can mine through English is not actually the most amount, right? Mining through related languages, that's the orange color, or through a bridge language actually allows you to significantly increase the amount of data. And this is just because of variability, right? Like in English, we only talk about a lot of stuff, but not everything. And so if you expand to cover other languages, like the actual content that people talk about, it becomes different, right? So if you think about, the Chinese drama shows that I really like to watch, like those are only discussed in Chinese, right? So actually expanding to cover other languages gives you more data. So it has like a very strong practical benefit as well. And so the major question that we compare in this work is like, okay, now that we have data for many-to-many translation, how does it compare to the English-centric strategy that we want to pivot away from? So we have three columns here. The first is translation to English, then translation out of English, and then translation through non-English directions. So a non-English direction, for example, would be French directly into Chinese. And the metric we show here is called BLUE, which is a rough metric of translation quality. And people use it because it correlates pretty well with human evaluation. So we have three baselines here. The first is bilingual baselines. So this is like a very intensive baseline to develop because we create one model for each direction. So there's like hundreds and hundreds of different models that comprise this first row. And you can compare this to an English-centric many-to-many model where you basically translate in and out of English. And that's the second row here. And so you can see that the English-centric models, they compare well to this bilingual baseline. The third row that we consider as a baseline is what we call pivoting. And so the idea behind pivoting with English-centric is like, let's say I want to translate from French into Chinese. I will create a translation by going from French to English and then English to Chinese. And that's what we call pivoting. And so that allows English-centric models to be able to produce non-English translation directions, which has stronger performance. So now what if we train with our many-to-many data set? So you can see here, the last row that I just added, many-to-many, it has similar performance to English and from English, but it has substantially better performance of translating non-English directions. And this is because for the first time, like we've actually supported these non-English translation directions directly with data in the model, so you can have significantly better BLUE score. So if you compare the many-to-many row with the English-centric row, you have like almost a 10-point BLUE quality improvement, which is very significant. For scale, most people think that like 1 or 2 BLUE improvement is quite impressive. So the next part of this work tackles like beyond data, how can we actually scale model size? So most commonly used translation models look something like this. The input text comes in into a sequence-to-sequence model. There's a encoder translation, an encoder neural network, which is often a transformer that reads the input text. And then a decoder neural network, which is often a transformer that produces the actual translation. So if I only want to translate from the red language into the yellow language, maybe this model capacity is sufficient. However, if I want the same model to represent 100 languages kind of in both sides, then essentially the model just doesn't have enough kind of capacity, right? If you think about neural networks as requiring some sort of memory or some sort of storage, some sort of capacity to represent all of the different languages, then if you want one model to do much more, you kind of imagine you have to scale the model size. And so people have really worked on these computationally very complex model parallel techniques. And these model parallel techniques basically explode the model size in terms of the width, but also the number of layers. So you could have drastically larger models. And so roughly how model parallel works is that you can think about the computation of a machine, like my phone, for example, as being limited by the amount of memory that's on the phone. So for my iPhone, it actually can only store so many images because the memory is limited. And so GPUs that we commonly use to train neural networks are exactly the same. And so when one GPU has too much to store, we can only store larger models by basically parallelizing across multiple GPUs. So instead of having one GPU store the model parallel allows the model to be sharded and stored across several different GPUs, which allows the size to expand. However, note that if you expand solely through this strategy by basically increasing the depth and the width, what you have is that every time you want to make a translation, every single one of those parameters needs to be activated. And so practically this makes translation incredibly, incredibly slow because now the model size has scaled so much. And so I want to provide kind of a reflection on what does this really mean, okay? So the scale here represents model size in number of parameters. So on the left, we have 418 million parameters, which is pretty large. When I first started doing research, that was inconceivably large. Now it's quite small. Now we go to 1 billion parameters, 11 billion parameters, and all the way to the right, the largest model that we work on in this paper is 32 billion parameters. So how does this actually map on if you think about a V100 kind of NVIDIA GPU? So if you want to go from 0 to 3 billion parameters, this actually fits on one GPU. And so if that's kind of the compute you have access to, then you would be able to train a model on one GPU. If you want a 11 billion parameter model, you actually need 4 GPUs even just to hold the model. Forget about training it efficiently, 4 GPUs required just to store the model. And if you want to go to 32 billion parameters, it needs 8 GPUs just to store the model alone. And so how does that reflect in terms of inference, right? So actually, if you go from 11 billion parameters, you still need one GPU to do inference, so you can produce translations with one GPU. So that's pretty ideal. But if you have a much larger model, you actually need more GPU to do inference alone, which means that practically, translation is a very applied problem. This is a big problem for actually producing translations. So what kind of performance do we get if we scale? So what we see here on the y-axis is blue, so our translation quality. And on the x-axis, we've broken down the performance of high resource, low resource, and mid resource translation directions in terms of model size. So the gray is the smallest model, and the light blue is the largest model. And so you can see for mid and high resource directions that improving the model size improves the translation quality. Whereas for low resource, there's not enough data, so the models tend to overfit, and you actually see a slight decrease in translation quality. And if you average across everything, you do see that as you improve the model size, the translation quality does improve quite significantly. But kind of a moment of pausing for reflection, we've kind of, drastically increased our compute capacity for, maybe 5 to 7 points of performance. So a lot of questions, to think about when you look at these papers that do a lot of scaling is is it really worth it? And so I think scaling is very important to show the kind of quality that we can get. And it is possible that for small models, we just can't improve the translation quality anymore because the model has some inherent limitation on its quality. But, we are kind of using so much more compute in order to achieve some performance. And so that's only accessible by certain people, right? We wouldn't be able to serve practical translations with such a large model. And so one of the things we turn to is how can we develop a more efficient strategy for training these large models that isn't just kind of naively expanding the width and the depth of the model? And so we call this language-specific mixture of experts. And the idea here is that the previous model, it's so slow because every time you want to produce a translation, you need to use like all of those gray boxes that we represent as layers in order to produce a translation. Well, what if we didn't have to use all of the capacity every single time? The idea here is that each language has some specialized set of parameters that are only activated for that language's translation direction. And so we represent different languages here with the different colors. And so if I want to produce a translation for the blue languages, I only use like kind of the shared parameters in gray and then the language-specific blue parameters. And the same thing if I want to do green language translation, right? Like I only use a subset. And this means that if I want to produce a translation from red to yellow, then I go through the common shared gray layers, but then I only hit kind of those language-specific parameters, which means that I have a large model, but each time I produce a translation, I don't need to use all of those parameters. And this kind of strategy is like 10x more efficient, and both in training, but also in inference time. So it drastically speeds, our ability to train the model, but also our ability to actually deploy translations. And so the benefits are that we get, languages have dedicated capacity to specialize, but we're at the same time can train a large model with only using a single slice at inference time. And this kind of scalability through sparsity has, a lot of scalability. So this strategy can easily scale to something like 100 billion parameters, which we don't actually explore in this paper, but, has great potential. And so when we scale the model size, so the first, chunk here is for dense models. So that's the model parallel strategy I discussed. So the first column shows kind of the parameter size from 1 billion parameters to 12 billion. And you can see the second column is words per second. So that's the amount of, training speed that we get. So because of model parallel and how slow it is to communicate between all those GPUs that's holding the model, you see just like how fast that words per second drops off. Then we have kind of the performance for low, medium, and high translation directions, as well as an average. And you can see that as we increase the capacity, we do get an improvement in overall performance, although it's largest for high resource languages. But now if we use the language-specific scaling strategy that I just discussed, so we start with our same dense model, but then we begin to add the language-specific capacity, 1 layer, 3 layers, or 6 layers per language. And so you can see that we have the same kind of parameter scaling from 1 billion parameters to about 10 billion parameters. But the words per second, it drops a little bit, but we don't get, like the 10x decrease or more that we would see with a dense model. And at the same time, we actually get better performance because languages get additional capacity to specialize. So this dense scaling strategy, it becomes very computationally intensive. So scalability through sparsity offers kind of a compromise where we have good performance, but also are able to train and produce translations at high speed. And so actually, this also has strong performance benefits. So for certain high resource languages, if you add language-specific capacity, you can substantially improve the blue score. So here I show the blue improvement with language-specific capacity. So this is kind of the delta. And so, for example, the first direction here we see is Chinese to English translation, which improves by over 2 blue points as well with this scalability through sparsity, because these major translation directions, they actually have enough data that they benefit from dedicated capacity in the model. So we have, an improvement in speed, but also you see the difference in translation quality if you have this kind of strategy. And so the major question is like, how do these models actually compare to the workshop on machine translation? So every year they run this translation competition for the academic kind of research world, So we've developed this kind of model, like how well does it actually compare? So here I list like all of the different years of the translation competition and kind of people's published numbers for that year. And now I show kind of all of the different directions and also kind of the comparison between the published numbers and in our numbers and the performance improvement delta. So you see that there are some languages where we don't improve. So for example, very embarrassingly, like our English to Chinese improvement has strongly decreased, even though I'm from China myself. But we have a large quantity of languages that strongly improve. So you can see there are some languages, for example, English to Turkish, Turkish to English, that improve by over 7 blue points. And on average, we improve by almost 2 blue. So one little caveat here is that in the WMT competition, people apply like tons of different tricks to their models. for example, like advanced techniques like noisy channel decoding. And so we could also apply that to our model, but just don't. So here, when we compare to published numbers, it's kind of comparable published numbers, and not necessarily like, you know, all of the tricks added, since we could also apply it to our model. And the last point that I want to discuss is kind of this multi-model ensemble strategy. So this is very interesting, and it's something where we hope to develop more in the future. And the idea is that if you have a many-to-many model, you know, you could have more interesting ensemble strategies. So what do I mean by ensembling? So a technique that works really well for bilingual translation, if you have translation from, for example, the red color to the yellow color, is that, you know, we're going to have 3 different models that we use, and we actually average their predictions. And this is commonly used in translation, and is one of kind of the tricks that I discussed on the previous slide that many people use. And so this is a trick because it really uses 3 models simultaneously, so it's not really like single model translation anymore. And so this triples kind of your computational cost, because you have to train 3 different models, but every time you want to produce a translation, you also have to use 3 different models. And the way it works is that people kind of average the weights of these 3 different models, so that when you produce the translation, you get kind of like an averaged agreement. And this is a technique people call ensembling, and it's very popular in machine translation. And so one thing that we're really interested in is multi-source self-ensembling. So if we have a model that can translate 100 different languages, then we probably don't need 3 separate models to do ensembling. We can do like ensembling with 1 model. And this is like a concept we call self-ensembling. And so instead of ensembling the model weights, we can kind of input 3 different languages and kind of ensemble at the level of the different languages. So just to wrap up this section, so there's a lot of challenges ahead. For example, what benefit can we really get from scaling? What are the possibilities for creating really large models efficiently? And, you know, if we want to improve the performance of specific languages, is multilingual really the right way? Or should we do transfer learning or some sort of specialized model? And so I'm going to discuss that next. And finally, yeah, we'll skip that slide for time reasons. So the next section I want to discuss is, what about pre-training? So a lot of people have come up with, you know, multilingual pre-training as a starting point. So if you've heard of MBART or multilingual T5, so these multilingual pre-training models, they don't use paired translation data. They just use monolingual data. And so, of course, paired translation data is much more rare in the world than monolingual data, because for monolingual data, it's like essentially any text in the world on the internet is data that you can use. And so are these models an alternative starting point for the development of multilingual translation models? And so there are several advantages to this. Like, first, it's just plentiful. Pre-training, it could also be easier than mining, for example. And then this pre-trained model, it can be used for a variety of different tasks. So once I create a translation model, essentially we use it for translation. But these pre-training models, you could be using them for anything. You can fine-tune them for a variety of different tasks. And so pre-training has this advantage. However, there's a kind of disadvantage, which is, first, the pre-trained models contain a fixed number of languages. So for example, if someone releases a pre-trained model and it doesn't contain Mongolian, like, what can you really do to fix it? It's already been pre-trained. Like, you can't like go and fix that because someone has open sourced it already. And then also, does it actually work? And so we mainly focus on this question of like, does it actually work? So first, on the first point, pre-training is actually extensible. So one experiment we did here was that we took a pre-trained model that someone had trained on 25 languages, and then we basically just downloaded it and continued pre-training, and we added another 25 languages. And so here you can see the performance comparison between these 2 different models on the original set of 25 languages. And you can see that even though we added an additional 25 languages, there's basically no performance difference between the 2 models, like the 25 version and the 50 version that we created. So actually, pre-training is extensible. So you could download someone else's model and just like add your own languages. So now, what about performance? So there's a lot of different strategies that we compare here. So we compare the bilingual models. So if you create a specialized model per direction from scratch, then we compare pre-training and then creating a bunch of different bilingual models, which was covered heavily in the original multilingual pre-training papers. And then we compare this also to 2 different multilingual strategies, multilingual models from scratch, and also pre-training to develop multilingual models. And so we compare here the performance delta compared to bilingual from scratch, translating into English. And so the first we compare to those 3 different model strategies I discussed. So the last 2 columns are multilingual from scratch and multilingual fine-tuning, and based on the number of training samples. So this is kind of low resource, from high resource, greater than 10 million sentences, to low resource, which is only like 4,000 to 10,000 training examples. And so you can see that the multilingual fine-tuning strategy, the bolded column, it works really, really well when you're translating into English. However, if you actually translate it out of English, basically multilingual models, they don't really have any performance improvement, and so you're better off creating bilingual models. And so this roughly shows us that pre-training, it works really well if you care about translation into English, because those pre-trained models have good representations, but translation out of English is still really, really difficult. And so our conclusion of this section is that, so pre-training helps when there's a large amount of monolingual data, but it's really not yet the solution for translating into low resource languages. And so the last thing that I want to end on is a few specialized techniques for low resource languages. And this comes through what we call iterative back translation. And so going back to how people create bilingual models, they go from this red language into this yellow language. And so the major question is like, well, what is the data that we use to train these models? And for low resource languages, like even our mining techniques are difficult to do at scale. Because for example, let's take a language like Inuktitut, which is spoken in northern Canada. There's just not a lot of content on the web written in Inuktitut. So even if we use the entire web, we just don't have a lot of data. And so the idea of back translation is that we strongly leverage monolingual data. And so let's say we have like a bunch of this yellow language example of target data that we can use. And so the idea is that we're going to train a reverse direction translation model going from the yellow language to the red language. And then we basically artificially augment translation data. So we take all of this kind of yellow data that we had around, we pass it through the model, and we basically create, red language data through this strategy. And then we can train a forward model on all of this back translated data. And so this is a form of data augmentation. So you can compare this to computer vision, where they basically like flip the image or like, add noise to the image or color the image differently. But this is kind of data augmentation for natural language processing. And it has a huge dependency on large quantities of monolingual data. So even though people have applied this strategy for great success on low resource languages, it only applies for directions where you have monolingual data. So, it doesn't cover the kind of extreme state of low resource. So the conclusion is basically we need better techniques for actual low resource languages. So just to wrap up for our entire talk, I want to reflect a little bit on where we might go in future directions. So first is tokenization. We want to build translation systems, but how do we actually, what is a sentence? So for example, in Thai, there's no period marker. So how do we actually tokenize? What about word tokenization? How do we actually balance different languages? How do we measure beyond blue? So throughout this entire talk, we've been talking about blue as like a single metric for translation quality, but it can't actually measure things like critical factuality errors or gender bias in translation. It doesn't measure, holistic translation quality that you might see as a human. And finally, data quantity is a huge barrier. So like I discussed, there's very few techniques that are developed for low resource languages specifically, and these crawl data sets are really noisy. There was just an audit study done that I've linked here. So this is like kind of an ongoing problem that we need to tackle. And lastly, I want to discuss, what does it mean to actually cover a language? So multiple different variants are spoken and accepted. So for example, my family, actually, we don't speak standard Mandarin at home. We speak kind of like a dialect of Chinese. And so that dialect of Chinese is obviously not covered by most standard translation systems. So we want to, how do we actually reflect kind of naturally the variation in languages and dialects? So thank you so much for listening. And all of the code and the models and data that we discuss in this talk can be downloaded from the PyTorch FairSeek repo. Thanks so much.
Thank you. Right on time. Perfect. And amazing slides too. So I think we have some questions.
Yeah, let me start with a very simple question. So I think this is used by human translators. So if you, especially translating literature, I mean, if you want to translate a novel from, I don't know, Russian to Mongolian, you look at how other people translate it into English or French or some other language, and then use that as an additional resource. Can you do that with machine translation? I mean, maybe you can think of an ensemble model where you go through different languages, where you go through English in addition to going through a family language, maybe.
Vishrav, yeah, feel free to chime in if you have thoughts. I think the first thing that comes to mind is indeed, there are definitely languages that are more close. So for example, Spanish and Catalan. So Catalan is spoken in one region of Spain. And so most of the time, the translators are actually used to translating from Spanish to Catalan. So if you want to translate from English to Catalan, even if they're fluent in English, it's like a much, much harder problem. And when they were translating Harry Potter, for example, like all over the world, they wanted to have like some tricks throughout the book that they like maintained through the different languages. So a lot of the translators for the different languages kind of worked together. And so one of the things that we're interested in this work is kind of that ensemble model where we ensemble multiple different sources that can leverage kind of the strength of nearby languages and that kind of language transfer that you're talking about. Vishrav, yeah, I don't know if you have other thoughts that you want to chime in.
Sure. No, that actually totally sums up really well. Another thing is one of the experiences we have had while creating the evaluation data set, especially the Americas NLI one that we talked about in the beginning. So there we were not able to find annotators who could translate, or translators who could translate from English to to Quechua directly. So we had to go through the Spanish data set first, and then we were able to find a lot of translators who could base the reference on Spanish and then translate into Quechua. So yeah, this problem becomes very severe in case if you are going towards more low resource domain.
Санадын комментод харагдж байгаа юу?
Yeah.
Би харуулах уу?
You be haруулж. Okay, so we have questions. Is it possible to combine multiple similar languages datasets, perhaps syntax, grammar somewhat similar, or will it just make it even harder?
I feel like this is a Vishrav question because Vishrav has worked so much on training data. What do you think?
Sure. So this has actually helped, to be honest, bootstrap some of the performance of translation. So I'll give an example. So in India, Hindi is written in Devanagari script, and the nearby country, which is Nepal, Nepali is also written in Devanagari script. So both of these languages are different, but then they share the same script, and there is a lot of vocabulary or lexical overlap between these two languages. And once we started moving towards building translation models or even collecting training data, we found that by simply concatenation of these two training data sets for building a Nepali to English model actually helped a lot in boosting the performance. And this and especially in these scenarios, finding similar data sets, similar languages can definitely help in bootstrapping the performance. Another thing is it also depends on how you want to combine the data set. So the first example I gave was a simple concatenation, but there are other ways also that people can try. So for example, if the script is not similar, then maybe projecting them into the same script. So for example, transcription, them into English, that's one another option. Or if two languages are phonetically similar, then maybe considering phonemes instead of normal text. So yeah, so there are multiple ways with which performance can be enhanced. Angela, you have any thoughts, any additional thoughts you want to share?
That was perfect, Vishrav. No, this is really your expertise.
Okay, so maybe you can, let's remove the screen now that we finished with. Could you explain what is the BLUE score and how do you calculate it? And is it the only metric for evaluating machine translation models?
Yeah, good question. So the BLUE score, it's roughly a measure of word overlap. So if my model produces a translation and a human produces a translation, the major question is well, how similar are those translations? And so the BLUE score, it basically separates the sentence into n-grams from 1 to 4 grams and calculates the overlap of those different levels of n-grams and then kind of averages the score. So roughly, so it goes from 0 to 100, with 100 being like exact match to human translation. Other human translators actually score around a 50. So if I have like 5 different translators and how much do they agree with each other, they don't agree 100% because there's often multiple different ways to translate a sentence, of course, like just like I can speak and say the same thing many different ways. Usually we consider a translation system is pretty good around 20 to 30 blue, and 10 blue is kind of like the minimum for producing an okay translation. So the scale we're working with is not very large. So actually most machine translation benchmarks compete on kind of decimal points of blue, like 0.5 blue is seen as like a strong improvement. Is it the only metric for evaluating NT models? Vishrav, I don't know if you have some of your other favorite ones, but people have also done kind of like character level comparisons or different modifications of blue, but they often correlate very strongly with blue. So since everyone already reports the blue score and we're all academics and want to compare to each other, people report blue.
And yeah, in academics, yeah, getting one blue score improvement is a big thing. It's hard. Okay. Oh, there was another question.
Yeah, our next question. Yeah.
Sorry, I don't know if it's just me, but I'm not able to see the question. It just came for, I think, 1 second, then it disappeared.
Yeah, same actually.
Yeah.
Okay. I was wondering if it's just me or.
Okay, let me try it again. Can you see it now?
No, maybe I can just read from here. Which one? Maybe you can ask.
Yeah. When it comes to tokenization for multilingual translation, what kind of tokenization techniques applied?
Oh, it has to be a Vishrav question. He specializes in this.
Come on. Yeah. So that's actually a good question. So in terms of tokenization, like, what people have done in the past and like including us, so that there are multiple ways in which you can tokenize. So one is like, in terms of simply splitting based on spaces, or like, if we have seen that in the past that like, it can lead to very large vocabulary. So there are other techniques that people have tried, which includes like going like beyond the word boundaries or like within the word boundaries, so that like, we have something like a word piece, or like, if you want to consider and go even beyond a word, you can even include like, one word and then like half of the next word, so that becomes like, piece of a sentence, so that sentence piece, or like people have even gone to the byte level for like, tokenization, like, because if you consider like not just even a single character, just consider like, each character as a byte, so that becomes like, byte level representation. So there are multiple things that people have tried, and this is an active area of research currently, that like which one constitutes like, a better part for multilingual translation. There is another slight point, which is like when we are considering learning these models for tokenization, like not the actual translation models, but like the models with which you can tokenize, like, is it a good practice to have a separate tokenizer for individual languages, or should we have a common tokenizer that can help in tokenizing like, any of the languages that you present to it? I mean, it's again like, both of these facts or points that I mentioned like have their own pros and cons. So the positive side of having a unified tokenizer is that you don't have to worry about like, what kind of language you are presenting, and in case if a sentence has phrases coming from multiple languages, the tokenizer would know how to tokenize them. And secondly, let's suppose if there is not enough training data available, or like training data, by training data I mean like data to train the tokenizer, then in that case, like, the data for low resource languages would be less, but then like a low resource language can make use of data from high resource languages if there is substantial amount of script overlap, as the example of Hindi and Nepali, and then and thereby like, identifying common subwords or like pieces within the sentence can be made use of in case if we are using a common tokenizer. Yeah, but then like in some cases the performance of low resource languages can suffer in case the high resource languages overpower them. Yeah, this is Angela for pre-training.
Okay. Oh yes, sorry. So pre-training is very, very popular in natural language processing nowadays. It's a general technique for text generation. And when I say text generation, I mean any model that produces text. So for example, kind of like the model that suggests, like when I text my mom, like it suggests to me like what word to type next. That's also a type of text generation. Of course, translation, where we generate an entire sentence, is kind of like one of the best examples of generation. And so the way pre-training works is that, let's say I wanted to produce a machine translation model. Traditionally, people have done it by having like bilingual data that represents the translation data. So it needs to be source target aligned in those two different languages. Yeah, and you create a specialized model for this. But the idea of pre-training is that we're going to create like a generic model and then apply it to different tasks by doing what we call fine-tuning on that different task. And so if you've heard about models like GPT-3 or Google's BERT model or BART, or there's a French version of these, like there's like one model for every single language now, basically. Well, the major languages, sorry, not Mongolian. And so these are all pre-trained models. And so they've had a lot of hype, particularly since maybe 2017 or so. And the way the pre-training model works is that they'll just take like really, really large quantities of data, not specific to any task. And so this really heavily can take advantage of kind of monolingual data on the internet. And so they download all of this data, and then they just train for the model to understand essentially text in general, mainly English text, but now, there's like a French version, a German version, a Chinese version, and so on. And so the way they do this is they basically take the sentence and they like kind of distort the sentence. For example, they like remove a word, or they like change the order of the words and stuff like that on the input side. And then on the target side, they need to reconstruct the sentence. So these models are only trained on this basically like sentence denoising or reconstruction kind of task, but then they can be then adapted to a lot of different tasks. So for example, the competitions on this like glue benchmark, the super glue benchmark, like these have all been like tests of pre-training quality. And so a lot of people have been like, wow, there's so much improvement in pre-training. Like, does pre-training basically solve every single NLP task? And in the last 3 years, basically people have carefully gone through all of the tasks and been like, not solved, not solved, not solved. And machine translation, especially low resource translation, is still one of those areas where we really haven't seen a huge improvement from pre-training.
Okay, so does many-to-many model powers Facebook translation service? I know it might be an apple to orange comparison, but in what setting Facebook machine translation models outperforms Google machine translation service?
Vishrav, any thoughts?
Sure. So honestly speaking, I'm not sure, like, in like what level of granularity we can probably go into this without not affecting like any of the privacy and legal concerns. But yeah, I can probably share such that like, so I can possibly talk about one thing, which is the translation models that we have at Facebook. Like, imagine that they have to work on a very unique domain, which is social media text, because like they have to be more specialized in order to handle all sorts of slangs or like informal languages or spelling mistakes than the general purpose domain model. So yeah, so like it depends on like what kind of data are you evaluating your models on. So for example, like it's very hard for the same model to outperform every other single model on different variety of domain data sets. Maybe in future we could advance to that state, but currently at least as far as my knowledge is concerned, that's not the case. So yeah, so possibly like you can assume that Facebook data that the Facebook translation models like they perform really well on the Facebook dataset. I don't have any numbers for comparisons for another datasets because we cannot use them for privacy concerns.
Yeah, I think another thing that makes it very difficult is, when we talk about these academic models compared to like Google Translation or Facebook Translation deployed, when you type something into Google Translate and then you hit translate, like you want an answer immediately. And the same thing for Facebook Translate. And so those models, they need to be small and they need to be fast to produce that translation quality. When we're talking about these kind of academic models, we have like, dedicated GPU that are just made for running them. So we can have like really, really large models. So a lot of times, for example, at the workshop for machine translation, that academic competition I was talking about, people are able to outperform Google Translate many different people actually outperform Google Translate. But that's because it's essentially unlimited amount of time available for you to produce the translation. But if you actually needed to produce the translation at the kind of speed people are actually used to in like our modern day internet, like I want everything immediately, right? So I'm not going to wait 5 minutes for a very slow model to produce a translation. So yeah, I agree with you that it's a little bit apple to orange, and also the domain effect that Vishrav talked about.
Okay, so the next question is more personal, I think. How did you guys start your journey on machine learning, and any advice for junior researchers? And what does it take to be a researcher at top tier tech companies?
Vishrav, life advice. What do you think?
Why don't you start on this one, and I'll second you like after with the afterthought.
Okay. It was a strange journey for me. So I didn't really know what I wanted to do as a career. So when my parents left China, they were doctors in China, but when they immigrated, they didn't have their medical license anywhere else, so they were not going to be medical doctors anymore. So I kind of felt like for my family, like I wanted to be a doctor, but when I went to the hospital, I became like very sad because there's a lot of sick people and it's very sad. So then I was like, well, I kind of studied medicine throughout all of college, and so now I don't really have anything else to do. So there's a new career path called data science. And I was like, okay, this seems kind of cool. It's a new thing, so people didn't really have a standard of what data scientists should be doing. So I was able to get a job at Facebook as a data scientist. But I didn't, like really feel a lot of passion for the data science area. And another thing is that I wanted to focus on something long-term. And so I found Facebook Research. At the time, they were looking for engineers to basically help, like work on research together. And so that's how I got started. Actually, Sina's paper on memory networks is one of the first papers I ever implemented. So it's like a cute throwback. Yeah, I don't know. I mean, it's a slow learning process for me. When I started in research, I didn't code very well. I mean, I studied medicine in college, so you can kind of imagine. We don't spend a lot of time coding in our biology classes. And so it was a very slow learning process. After I was an engineer for a while, I felt that, I wanted to do more research, but I didn't really have a lot of my own ideas at the time. And so I felt like, how can I actually like produce my own papers if I don't really know? And so I decided to change to a PhD program, also to kind of go back to school, get more training, and really kind of like challenge myself on like, can I do more? Can I have my own ideas? And over time, like I learned and got better. So for me, it was definitely like very slow learning over a large period of time. And I think the other thing is that, you don't always know what you want to do in life. I definitely experienced that myself. But the more I did research, I found the more I liked it. And so now I think I'm like pretty excited. Vishrav, any thoughts?
Sure. I mean, like I'm actually surprised to know that a lot of my life journey is also very similar to Angela. So, like to begin with, even both of my parents are doctors. So I also grew up with this ambition of like becoming a doctor, and did not even study computer science till 12th grade because there was an option in India like I could choose computer science and biology, and I chose biology because I was so passionate about it. But then like when I was in high school and like towards the end of finishing and completing it, I kind of got this inclination towards engineering, and specifically computer engineering. Credit goes to some of the other relatives I have in my family. So that's when I just joined like an engineering college and focused on computer engineering. I never even thought that probably I'll go for higher education or even graduate studies after that. And then like immediately after my undergraduate studies finished, I took up a job in hedge fund, and like started focusing on, it had some level of machine learning in terms of like building forecasting models for the trading analytical engine, but I primarily focused on large scale distributed systems. And in 2015, when I moved to the US, because my parents and I immigrated here, I thought of like starting my master's at CMU, so that like I could possibly learn more and dive deeper to understand a particular problem or not. And I wasn't sure initially if I should be going for PhD or not, because like sometimes when you are working in a particular area, I felt like I'll probably go get some more industry experience and then rethink about getting a PhD. So that was one of the motivation. that I joined Facebook. Started off doing on machine learning, and then I joined this NLP team in Facebook AI, and started working on more applied research problems. So by applied research, I mean that like you still do research, but then they have to be valuable to the end Facebook product in some or the other way. And recently I've started focusing more on research. Like for that, like we don't have to worry about like how productionization or end product would look like. But yeah, like, so over the time I've realized that my journey has always been evolving, in the sense that starting from a point that I did not know what I wanted to do, and like, going into a place where like, I'm exploring new directions on a yearly basis. So yeah, that's what I would say.
Well, thank you so much. I think this is maybe the great question to end, actually. Yeah. I didn't know, Angela studied medical. Well, I have so many questions to ask you now. And it's nice to hear that, yeah, people didn't know what to do at some points, It feels very familiar. And today's talk was great because it's about lower source language translation, which is really important for Mongolia. The people in Mongolia, even not, who are not interested in machine learning, because they're going to use it every day if it works. And, learning English was definitely a very difficult experience for me. So yeah, thank you so much for giving this great talk. And yeah, I think the language translation will improve in future, and we don't have to learn a lot of different languages.
Thank you so much for inviting us and for all of the great questions.
Okay, so yeah, I think we can end now.
Thank you very much.
Thank you.
Yeah, we hope to see you in Mongolia when the COVID pandemic is over.
Oh yeah, always welcome.
Thank you.
Thank you so much.
Okay, thank you.
Thank you.
Bye.